or a spectral monitoring system to classify satellite downlink systems. Next slide. For a problem statement, previous research has been used to classify RF signals without data preprocessing with an accuracy of around 80% on satellite downlink data. Different features such as Doppler shifts have been used to build invariants in the models to make the models be able to classify satellite downlink systems in a variety of conditions, such as a satellite downlink signal experience a Doppler shift, pre-processing the raw IQ data, such as center cropping and padding the samples into equal sizes, has improved model performance. And then also spectrograms, which are frequency amplitude plots in a single point in time, have also been used to identify short bursts of signal. Next slide. For a little bit of background, CNN classifiers have been used to classify modulation types of RF data from RF drone transmissions. And CNN classifiers have been used to identify different commonly used modulation types used in data communications. And CNN classifiers have been used to classify modulations of IQ data. Pre-processing has been applied to the IQ data of RF signals to improve performance. And then Doppler invariance was added to a Doppler-aware CNN model to classify IQ data. Next slide. For the related work, I looked at 3 different studies. The first study, Bagchi and Hutchinson, looked at adding Doppler invariance to a CNN classifier that classified RF data. The second study looked at the EMOD, looked at classifying modulation types, and then the Ilyusuf looked at adding pre-processing to the IQ data in classifying IQ data from RF signals. Next slide. For an approach, data augmentations, including Doppler shift simulation and time shifting, were applied to the training data to build Doppler and temporal invariants. Samples were pre-processed into equal size by either zero padding or cropping the data to make them into equal size samples. A 1D residual network classifier was used since this allows for deeper training of the model. And the program is in time domain. Convolutions are performed across sequential times samples, and the classifier uses raw IQ data. Next slide. For the design of the CNN classifier, I used a fairly generic CNN classifier architecture with input, convolution, activation, batch normalization, pooling, dropout, residual blocks, flatten layer, dense layer, and a final output layer that uses a softmax function to determine the most likely label. The residual blocks skip connections through the in the model that allows deeper training of the model to allow a larger neural network to be used. Next slide. And then for the pre-processing of the data comes from multiple sources, including a publicly available data set and house sources collected in-house from UHF and a KU band antennas. These are all converted into NumPy samples with two channels, I and Q, for the phase and quadrature of the data. The data is then pre-processed, and then data augmentations, including Doppler simulation, time shifting, Gaussian noise, and amplitude scaling, are added to the data. And then they're all converted into the same format when they are used by the classifier. Next slide. For the implementation, the data was converted into NumPy samples of complex numbers from compressed raw and IQ files. The data is then processed into equal sample size by either cropping or zero padding the data. The data augmentations, including Doppler invariance, time shifting, Gaussian noise, and amplitude scaling, are then applied to the data. And the 1D ResNet classifier was used as the classifier model. The residual blocks are used to add original RF features back into the transformed features. And then a ReLU activation function was used with to be able to identify nonlinear patterns in the data, while batch normalization was used to stabilize gradients and improve convergence. Next slide. For the data collection, the data was collected from various sources, including the public dataset and in-house recordings of satellite downlink. 17 satellites labels were used with a distinct signal structure. The signal structure is determined by the modulation type of the satellite. And then a custom apparatus was used to collect Starlink beacon telemetry signals that demonstrates that this classifier can work, is frequency agnostic. It can work across multiple satellite frequency bands. The recordings are stored in a raw IQ format and then are converted into NumPy format. Next slide. So here's an example of some of the signals, like the NOAA is of in-house recordings, which is that top figure there. It has a very distinctive shape. This downlink signal downlinks low resolution imagery data, and then the Starlink signal. That's actually multiple Starlink signals in a line. See kind of under the graph how the feedback is slanted, shows a strong Doppler shifting, since these satellites are moving at high velocity, and then it has a very apparent Doppler shift. Next slide. So for the amplitude scaling, gain scaling was applied to simulate variations in signal strength, and then log uniform random scaling was applied to the I and Q channels. This was to resemble real-world conditions that the signals would often experience. Next slide. For the Doppler simulation, frequency and phase rotation was applied to the IQ data to simulate Doppler shifts, which was applied during the pre-processing step. And this or adding Doppler simulation to the data set was demonstrated in previous work from the key references. Next slide. So this is a summary of the precision recall per label. The classifier was able to identify labels that had a sufficient amount of data with high accuracy. Next slide. And then we have the precision and recall curves with areas under the curves for these labels, and a confusion matrix where the true and predicted, the true label usually matches the predicted label indicated by the diagonal pattern in the confusion matrix indicating good performance. Next slide. For the training and validation loss, the model stabilized after 40 epochs, where the model experienced little invariance, and the training and validation difference between the training and validation loss was minimal. Next slide. For the overall accuracy, the classifier had high accuracy with 96.77%, and then balanced precision and recall performance. The macro precision is the precision if you took the average of the precision or recall per label, regardless of the number of samples. And then the weighted precision and recall is weighted to where samples that have more numbers of samples have a higher weight. And these both also had balanced performance. Next slide. For the findings, the model achieved a high overall accuracy, where predicted labels usually match the true labels, and the model produced a high precision and recall performance for individual labels with sufficient testing and training data. Some of the data that was in the public data set only had a few samples per label that did not produce enough data to allow for sufficient training. Next slide. A 1D ResNet classifier was effective in classifying IQ data from satellite downlink transmissions at a high accuracy with balanced precision and recall performance. The data augmentation step made a modest improvement to overall macro precision and recall when compared to when the model was run without the data augmentation, although the weighted data augmentation was roughly about the same when the data augmentation was included or was not included. And then some modulation signals from satellite downlinks that have previously not been characterized by CNN classifiers were classified by this research. Next slide. For future work, I mainly want to build a data pipeline that would from the satellite antennas that were used to collect the data to create an automated process that would pre-process the data into the NumPy samples that could be then used by the classifier, and then expand the classifier to be able to be used with perhaps hundreds or thousands of labels as opposed to just 17 labels. And then be able to make improvements to the model as the number of labels grows. And then also the model could be tested in noisy RF environments where there's many interference sources. Next slide. For the demo, it's a video. If you could click on that. Project of IQ data and
just quickly, are you able to hear the audio or not? Okay.
I can hear it. Oh, I think you have to press play on it, or maybe
It's
rewind it.
playing on my end, so it's not showing on your end. Is that what you're saying?
Oh, I don't hear it playing.
Okay, so it's probably an audio bypass. I'm not sure how to do that. Hmm. Anyways, let's
Signals from
see.
satellite
I hear
are
it.
downlink. Here we have a Starlink beacon signal with a highly apparent Doppler shift. Here we have the NOAA APT signal on the left-hand side. This is the data collection apparatus for the Starlink telemetry beacons, taking signal from a LNB converter and then using an SDR to turn this into IQ data. This is the CNN classifier code running on a GPU optimized EC2 instance. When it is finished, it'll produce the accuracy statistics and figures. A 1D ResNet classifier is used with an input stem, residual, flattened, fully connected head ReLU, head dropout, linear output layers, and is evaluated by a softmax function. Program finishes, this produces an accuracy report that reports precision and recall, and this including the overall statistics, and then a breakdown by the individual classes. It also produces a confusion matrix showing the predicted label compared to the true label and precision and recall curves with area under the curve calculations.
Okay, I think that's the recording.
Yeah. And then references. And then questions.
Thank you. Any questions from the room? Okay, if not, then I'll ask my first question. I have controller for slides. So I was curious about the data augmentation. Like were you able to implement this data augmentation? And it looks like it improved by quite a lot.
It improved in the weighted or the macro precision and recall. I think just because I had a few labels that had a lot of samples that were already identified by the classifier, and this was applied on the pre-processing step by the augment IQ function. So this was basically just building a data set that had more varied conditions of what it might encounter in the real world.
Nice. Okay, I think I have one more question that I was curious. Oh, I think because again, this is not my domain, so I'm pretty curious on what is the value of, let's say, yeah, this is working, right? And you're able to identify which frequency right now, right? What is the value that you wanted to, is it something you want to sell as a product, or it's something, sure, as a hobby, but what does it help with?
My work has a global network of satellite ground stations that there's potentially some spectral monitoring contacts, and then also to be able to identify satellite downlink signals in a crowded sky of if you look at downlink of just like a broadcast, you could be getting all kinds of things from local radio stations to random, I don't
I
know,
see.
TVs interference to know what a satellite downlink is and being able to distinguish that from background noise.
I see. Okay, so let's say now I'm able to identify which signal is which, so then the receiver is more effective. Is that what you're saying? A receiver could be more effective on just getting the certain signal from certain satellite? Is that
To be able to determine uh, what signals are present in the sky, or be able to determine on a pre-known data set that something is satellite downlink signal versus some other source of interference.
And this just another like curious question with like not a lot of knowledge is, let's say we identified there's a lot of different satellites are using these certain frequency. Would it be a strategy for, let's say, another satellite or another thing that would try to use a different frequency? Would that is
Uh,
something not
yeah,
happens?
normally they get
Uh,
licensed on about the same frequency, like
got it.
400.5 is kind of designated as a satellite downlink signal in UHF. So it could be used to identify if a satellite operator was uh, illegally downloading on some signal that they weren't
Oh, okay.
supposed to, or it could be used to identify if a satellite's still broadcasting or not, if it was in doubt, if the satellite was still working or.
Thanks. That's a really clear explanation. Okay.
Mhm.
All right. I think that's all for today. Thank you, everyone, for your presentations, and good luck. And see you again.
Okay,
Bye.
thanks everyone.
Bye.
Thank you.
Bye.
Thanks so much.
Bye.